So Andrew just asked a question about what happens to delta U in an isothermal process. So Andrew, is it okay if instead of delta U, I think about du, which is small change, okay? So let me write down things. And at any point, if you think, wait a minute, I don't buy that, then you tell me, okay? So du, now we can think of U as a function of VTP for a constant composition system, fair, right? But we know at equilibrium, we don't need to specify all three of them separately. Specifying only two of them is sufficient. We can choose any two. We can choose volume temperature, we can choose temperature pressure, we can choose pressure volume. Let's see what happens if we choose V comma T. If we choose V comma T, and again, you could derive relations with others. There is nothing special about this one. This one connects to heat capacity, and that's why we prefer it. So if you think about U as a function of V and T, then we can write down du as partial U by partial V at constant T multiplied by dV plus partial U by partial T at constant V multiplied by dt. And this becomes du. This second term over here, partial U by partial T at constant V, we saw is equal to the heat capacity. This is CV, heat capacity at constant volume multiplied by dt. And this first term, partial U by partial V at constant T, has a name. We call it internal pressure pi T because it's at a constant temperature multiplied by dV. So the question Andrew asked is, why is it 0 for an isothermal process? So clearly, isothermal process for a general material or a chemical, for a generic chemical, pi T won't be equal to 0, right? dt will be equal to 0 because we are talking about isothermal process. So for a generic material, du at constant T, that is isothermal, is going to be pi T multiplied by dV, which in general is not going to be equal to 0, unless your isothermal process also happens to be constant volume, right? But isothermal process for ideal gas, we have to think about pi T, which is partial U by partial V at constant T. And we know that U for an ideal gas is given by number of degrees of freedom, let's call it F, multiplied by R by 2, right? Per mole of ideal gas. It is number of degrees of freedom. I could write it NDOF. I will just write it F for now. So this is number of degrees of freedom. So if you think about partial U multiplied by, I missed something, right? It's RT. If I look at partial U by partial V at constant T, that's 0. So for an ideal gas, pi T is equal to 0. Therefore, for ideal gas, du is equal to CV dt. And this is why if dt is equal to 0, du is equal to 0 for an ideal gas, not in general. Now, if this is, if Andrew, you really understand this, you should go back home and try to show a similar relation for dH, that dH is equal to Cp dt only for an ideal gas. We get the same thing for enthalpy. So for an ideal gas, isothermal is equal to iso internal energy and it is also the same as isoenthalpy, right? Because dH is also equal to 0 for an ideal gas. These relations are true only for an ideal gas. If you don't have an ideal gas, then you have to think about the internal pressure for du, and for dH, you have to think about the Joule-Thomson coefficient, right? Which captures how does temperature change with pressure. Good, so this was a good question. This is subtle. People get confused about it. I know professors here who get confused about it after many years of taking thermodynamics. This is not obvious. Any more questions? So thanks to Andrew asking a question, the midterm became just slightly easier now. Okay.
Can you go in again how for the ideal gas, they're isoenthalpic?
Oh, that's for you to think about.
Oh.
I just showed that du is equal to Cv dt. Yeah. It's the same argument. Go through it for dH is equal to Cp dt. It's exactly the same argument. The only difference will be that instead of u as a function of Vt. Now you will think of h as a function of pt, okay? And write down dh, something multiplied by dp plus something multiplied by dt, and the same argument. Your best friend, once again, will be that u is equal to FRT by 2. Use this relation and you should be able to prove that. Do that. I might even ask it on the midterm. No promises. Okay, any more questions? Oh yeah, midterms becoming easier and easier. Go ahead. Yeah, that stuff is confusing. And it's really, it becomes a bit beyond the scope of 481. It's better for 482 to talk about how the degrees of freedom arise. How does vibration contribute? How does rotation contribute? In your exam, if it involves degrees of freedom, I will tell you how many degrees of freedom does the molecule have, okay? You won't have to calculate it. I will tell you. But you need to, that doesn't mean the problem will be easy. And we will use that today. What you need to remember is oxygen will have different degrees of freedom than sulfur dioxide, than sulfur trioxide, and it might depend on temperature, that it changes depending on how different modes get activated, right? And quantum mechanics starts to matter. Go ahead.
Is there any geometric way to think about the computer?
What do you mean by geometry?
So with pressure, I can think about it as the number of impacts over a given point in time. With kinetic theory, I can think about it as like taking that delta T slice and then multiplying by half.
Yeah, okay, so I can't think of a very direct way. As I said last time, it's really, it's bookkeeping. How much does the internal energy change if the volume is allowed to change? It's bookkeeping. So whether that's geometry or not, I don't know. I mean, it's bookkeeping. That's the intuition there. Okay, at this point, your midterms have become satisfactory easy. If you have more questions, ask me. Any one more question before we proceed with material today? Okay, good. So by the way, the material on midterm will be till next Wednesday. So anything that is covered today, Monday, Wednesday will be on the midterm. The material on Friday will not be in the midterm. Which means the second law of thermodynamics will be a part of the midterm, because that's what we will start with next time. Okay. We will start just with a little bit of second law of thermodynamics. The midterm primarily will have questions related to first law of thermodynamics. I will probably have one easy question about second law. Mostly it will be first law. So let's talk about an adiabatic process. So we saw different types of processes, right? We saw isothermal, we saw isochoric, we saw iso-internal energy, we saw iso-enthalpy. Ideal gas is boring. Many of these processes become the same. Isothermal is the same as iso-internal energy, is the same as iso-enthalpy. For generic materials, these processes are all different. So one process which is also quite common is an adiabatic process. And adiabatic process is in fact at the heart of designing engines and variety of things. So adiabatic process is one that happens without exchange of heat from surroundings to system, or without just exchange of heat from surroundings. No heat is lost to the surroundings, no heat is gained from the surroundings. So this means that delta Q is equal to 0. Notice this could be a reversible adiabatic process. This could be an irreversible adiabatic process. Okay, when the change is happening, your system might be expanding reversibly or irreversibly. We are not talking about that. So this could be reversible or this could be irreversible. Adiabatic is not always reversible. It could be either. So let's try to visualize this, how it looks like. So we have some sort of, this is something that is thermally insulated. So delta Q is equal to 0. And in it, you have a gas, which is at volume VI. And something is going on inside. For example, the gas is allowed to expand to volume VF, from VI to VF. So example is adiabatic expansion of a gas. Now this could be reversible, this could be irreversible. Reversible means that the pressure experienced by the gas is the same as the pressure the gas would have if it was following an equation of state. So irreversible processes in general are hard to deal with. We will talk about irreversible processes when we get to entropy. So after the midterm, we will be talking a lot about irreversible processes and what distinguishes a reversible process from an irreversible process. So for now, specifically, let's focus on adiabatic reversible expansion. Okay, and this could be compression also. It just instead of VI, let's imagine we started from a VF and we are coming back to VI. So it's a general framework. So the question now is, so this is a thermally insulated container. So no heat can be lost. Somewhere in some books, you will see adiabatic process defined as no heat or mass can be exchanged. I find it confusing. I would rather stick with the definition, no heat can be exchanged. So if it's a thermally insulated container, we want to figure out as the gas expands from VI to VF, how do pressure and temperature change? And we are talking about a reversible expansion. If it was irreversible, it won't make much sense to talk about pressure because we can only talk about the external pressure that is being imposed, right? What are we talking about? What is it that is changing? We don't know. We're talking about reversible expansion. So how should we start to do this? What equation should we use to start to solve this problem? If I gave you this problem, this is something which you are well equipped to solve right now, given how much thermo you have done. There is no new material that will be needed to solve this part of the problem. Go ahead. Let's even simpler, first law of thermodynamics, right? So let's start with first law of thermodynamics. Delta U is equal to delta Q plus delta W. And what you said is pressure volume work, right? So here we can say delta Q. What is delta Q for this process? 0. What can we say about delta W? Minus P dV, right? So let's write down the differential form. du is equal to d0 minus P dV. And why can we write P and not P external? It's a reversible process, right? P external is equal to P due to reversible change. So in a certain way, these adiabatic processes look nice. When you start doing the math, you are like, oh yeah, this is so much nicer. I don't have to deal with so many terms. It's simpler. But how do we proceed from here? Let's go to the next page and write down our equation. So we have so far du is equal to minus P dV for adiabatic expansion / compression reversible. Adiabatic, oh, that my reversible looks terrible. Reversible expansion compression. So you're expanding the gas so slowly that, so how is the expansion happening? There must be a piston that is being pulled inside, right? That is moving up. And the pressure of the piston as it is moving up is always the same as the pressure of the gas. So it's reversible. What can we do now? Can we proceed any further? We can, so we will have to assume some equation of state without to proceed any further. If we don't assume any equation of state, then we are kind of stuck. So for this problem here, let's assume ideal gas equation of state. I could make wonderful exam problems where I ask you to repeat the whole thing for van der Waals equation of state, your hint at future problems. Let's assume ideal gas equation of state. So for ideal gas equation of state, we know PV is equal to nRT. But before doing that, let's think about equation 1 and think of U as the function of volume and temperature. We know something about an ideal gas. We know something about du that thanks to Andrew, we went over in great detail at the beginning of this class. What do you think, Andrew? What should I write du as for an ideal gas? Ideal gas, it's not isothermal. Du is equal to CV dt for an ideal gas, right? Because pi t is equal to 0. So for an ideal gas, so just to rehash, this is partial u by partial v at constant t dv plus partial u by partial t constant v dt. And this term is actually not the full term, but this term is 0 for ideal gas. And this term is CV. Therefore, du is equal to CV dt for ideal gas. So we are getting somewhere. Let's call this equation 2, 1 plus 2. If you put this in the left-hand side of equation 1, you get CV dt, and the right side is minus P dV. This is true only for an ideal gas. If it was not an ideal gas, you won't be able to write this. Your differential equation will be way more complicated. It can be solved, but it will be complicated. We have a simple equation now. Again, keep your eyes on the prize. What we want to do here is we are changing from volume initial to volume final, and we want to study how will the pressure and the temperature change during this process when the heat change of the system is 0. So we have CV dt is equal to minus P dV. What should we do next? Again, we are working for an ideal gas. So let's substitute for P, right? Let's substitute nRT by V. Why should we do that? Because the left-hand side has dt, the right-hand side has dV. And if you're solving these equations, why do you want pressure? You want to have temperature and volume on each side, right? So you can do the integration. So CV dt is equal to minus nRT dV by V. And this T can be taken to the left side. CV dt by T is equal to minus nR dV by V. And now we can integrate this equation. We know that the volume is going from volume VI to volume VF, and the temperature is going from temperature Ti to some temperature Tf. And we don't know what are Ti and Tf. Maybe we know Ti. We don't know what is Tf. So now we can calculate this directly. What is this integral on the left-hand side? Anyone remembers the integral of dx by x? Log of x, right? Don't forget that one. So this means ln Tf by Ti is equal to minus nR ln Vf by Vi, or Cv by nR. Let's bring out this. Oh, let's take this nR to the left-hand side. Cv by nR multiplied by ln Tf by Ti is equal to minus ln Vf by Vi. Let's give this Cv by nR a name. Let's call this as C, the small letter C. Nothing to do with the speed of light. This is just our symbol C over here. Okay, so C is defined as heat capacity at constant volume divided by nR. So what does this mean? Let's go to the next page. I'll write down this equation on the next page again. So we just showed that Cv by nR multiplied by ln natural log of Tf by Ti is equal to minus natural log of volume final by volume initial. And this thing we called as a C. So C ln Tf by Ti is equal to minus ln Vf by Vi. This can go and become a power over here. Therefore, ln Tf by Ti to the power C is equal to, and this minus sign can go inside, and this becomes ln Vi by Vf. So now we can get rid of the ln's. So Tf by Ti to the power C is equal to VI by VF, or VITI to the power C is equal to VFTF to the power C. This is an interesting equation. In other words, volume multiplied by temperature to the power C is equal to constant, right? Initial state, final state, this has the same value. And the final state could be anywhere. You're going reversibly. It could be anywhere along the process. Is equal to constant for adiabatic, reversible expansion of gases. And by expansion, I mean expansion or contraction. So this is an interesting relation. And our heat capacity shows up here directly. Heat capacity is the power that goes up here. So now you can see why that degree of freedom relation that I spoke about matters, right? If you have oxygen undergoing this expansion process, the power that you will have in this equation will be different for if you had ethane undergoing the expansion process, right? And you can go and look up the number of degrees of freedom and you will get the correct power over here. When you get this correct power over here by looking up the degrees of freedom, should you really put a lot of weight into this equation? Should you trust your life over this equation? If someone told you, well, I have made a machine where the gas is expanding in a certain way, you sit on top of it, and we will just make it go so high that when it gets below you, you won't get smashed against the ceiling. You'll be like, yeah, my equation is right, I trust it. Would you put that much trust into this equation? Why or why not? It's for an ideal gas, and you know it's probably not an ideal gas, so don't put your life on this equation. It's a decent equation, but it's assuming an ideal gas. For a real gas, this equation tends to look complicated. And for a real gas, the complication will come from two parts. First of all, we cannot use, I will call it henceforth, Andrews equation. Is that fair? Okay, you cannot use Andrews equation. du is equal to CV dt. That applies only for an ideal gas. And you cannot use PV is equal to nRT. So there is a recipe for how to proceed, but you will have to do way more math to get the equation of state. Any questions about this? Okay, so now we derived how the volume and temperature change during an adiabatic process. A similar question can be asked for how does the pressure change during an adiabatic process, right? So this tells us how does the temperature change as you are changing the volume. The question is, let's number this equation. Let's call this equation number 4. How about pressure change during this process, during this adiabatic expansion or compression of gas? How should we proceed for pressure? Any idea? Right?
Substitute one of the variables for CVNRT and then C withdrawal.
So which value should we substitute? It's better to substitute temperature, right? Because we were given that volume changes from VI to VF. So what he's saying is that we know PV is equal to nRT, or temperature is equal to PV by nR, right? Let's call this equation number 5. Actually, we can go even simpler. Let's skip equation number 5. Sorry about that. The simpler way to do it, what we should do is to think that this means that pressure initial multiplied by volume initial should be equal to nR multiplied by temperature initial, correct? And pressure final multiplied by volume final is going to be nR multiplied by temperature final. This is not the only way to get pressure. You could directly substitute temperature in that and still get it. This is slightly less painful mathematically. So if you divide both of these things, what do you get? You get PI VI by PF VF is equal to TI by TF. Fair enough? For an ideal gas, this is always true. This is not assuming anything. This is just true for an ideal, well, apart from the ideal gas assumption, this is not assuming how the process was. So let's call this as equation number 5. I'm going to write down 4 and 5 again on the next page because we are going to use it. So let me just take a moment so you can copy if you have not copied. And I will write it down on the next page, so not much is lost. So equation 4 was VI TI to the power C is equal to VF TF to the power C. And equation 5 is PI VI by PF VF is equal to TI by TF. So we can use equation 5 in equation 4 now, right? We can say that this must be, so equation 4 says that VF by VI. So if you take this VI and bring it to the denominator over here, it says VF by VI is equal to TI by TF to the power C, correct? This is just a restatement of equation 4. Equation 4 is the same as saying this. Therefore, equation 5 can now be written as PI VI by PF VF is equal to this thing. And what is this thing? This thing is VF by VI to the power 1 over C, right? How did I do that? Here I said that this means VF by VI to the power 1 over C is equal to TI by TF. Fair enough? Everyone happy with that? It's just algebra. It's nothing profound. Therefore, let's call this equation 6. So equation 6 has VI by VF on the both sides. So this VI and this VI can be brought together. So this VI can be taken to the left here, and this VF can be taken to the bottom here. So what do we get from that? We get PI VI to the power 1 plus 1 by C by PF VF to the power 1 plus 1 by C is equal to 1. So it looks, okay, we have a relation, but this 1 plus 1 by C is kind of peculiar, right? Remember what was C? C was CV by NR. So let's see what we can talk about this 1 plus 1 by C. And this is where your Karina, right? Karina's favorite degrees of freedom will show up. Okay, so if you have any questions about that, you can ask Karina. No, it's okay. You don't have to bother Karina. I'm sure she will help you. So let's think about this 1 plus 1 by C. We give it a name. It's so important. We call it gamma. So we use a Greek symbol for it. Okay, gamma. Gamma is defined as 1 plus 1 divided by C. And let's see what we can talk about this. So this is the same as C plus 1 divided by C, right? And what is C? C is CV by NR. So this is CV by NR plus 1 divided by CV by NR. Or gamma is equal to CV plus NR divided by CV. Does the numerator look familiar to anyone for an ideal gas? It does? Cool, but what is it? We saw it a bit sooner than last year. I mean, your answer is correct. Yes, it does look familiar. Even simpler, what heat capacity is larger than CV? CP. Remember, for an ideal gas, we showed it was a practice problem on the Slack channel that CP minus CV is proportional to R. CP minus CV for an ideal gas is NR. Remember? CP minus CV is equal to NR for ideal gas. We showed this two classes ago. 2 or maybe 3. CP is always greater than CV, right? I think, who was it? It was Stella or someone else who made that argument that CP is always more than CV, right? You're giving heat to the system and the system is expanding, doing work against the atmosphere. So CP minus CV is equal to NR. And we even proved this. Let me remind you how did we prove this. The proof was very simple. We said CP is equal to partial H by partial T at constant P. And it's simple enough that, see, I'm not looking at my notes, I'm just writing it here. So also I think about thermodynamics all the time, so it's a bit unfair. H is equal to U plus P, right? For an ideal gas, PV is equal to NRP. So Cp becomes partial U by partial T at constant P, right? We can put this U over here, plus partial NRP by partial T at constant P. Anyone remembers now how we did this proof? Is equal to partial U by partial T at constant P plus NR. This is not CV, right? This is not quite CV, but for and we are working only for an ideal gas in this thing. For an ideal gas, U is equal to number of degrees of freedom multiplied by RT by 2. Therefore, partial U by partial T at constant P is the same as the partial U by partial T at constant V. And how much is both of them? They are same, but can we write down what is the value for this thing? FR over 2, right? This is FR over 2. So this thing is partial U by partial T at constant V plus NR. And what is another name for partial U by partial T at constant V? CV. So this is CV plus NR. So this is how we showed that Cp is equal to Cv plus NR for an ideal gas. In general, Cp is always more than Cv, but in general, Cp is not Cv plus NR. In general, it's something else. And the derivation, for those of you who are watching the video later, I wrote the derivation on the blackboard. This is exactly something we did in class around 2 classes ago, this whole thing. So we got something. This gamma that we just defined is actually the ratio of Cp by Cv for an ideal gas. Okay, otherwise it won't be true. So this is only true for an ideal gas, all of this, what we are doing over here. And sometimes in chemistry, people forget later on when you start using these equations, you forget that you're assuming an ideal gas to do it. If it was not ideal, it will be a bit stuck. So in other words, we have just showed that Pi Vi to the power gamma by Pf Vf to the power gamma is equal to 1 for an ideal gas doing adiabatic expansion or compression, or PV to the power gamma is equal to constant for adiabatic reversible expansion. So now we can summarize both our equations. So we had equation number 4 earlier, and now we have this equation number 8. So we can write down our equations for, this is page number 5, page number 6. Summary of this material is that PV to the power gamma is equal to constant. Oh, you want me to shut up or what? And Vt to the power C is equal to constant. And both of these exponents, again, this is not true for any process in general. This is not true for a non-ideal gas. So anytime you get a process, this also happens in chemistry a lot. You get a process where you have to calculate the volume temperature change. You don't know what to do. You directly go and use this equation. I mean, if I got $1 for every time I have seen this happen, I would be very, very rich. Don't do that. This is true only for adiabatic reversible change in ideal gas. Okay. And what is C? C is equal to heat capacity at constant volume divided by NR. And what is gamma? Anyone remembers? Cp by Cv, right? It's the ratio of heat capacity. Wikipedia even has a full article on the ratio of heat capacity because it matters so much for engineering. Keep in mind, even though it matters so much that it has a Wikipedia article on it, I mean, you could have a Wikipedia article on yourself. I could have a Wikipedia article on myself, right? That's no claim to fame. But the reason people use it, because for ideal gas, we can calculate it. It's easy to do that. Let's see if we can express gamma directly as a function of the number of degrees of freedom. So I keep emphasizing that in this class, I'm not going to bother you too much with calculating the number of degrees of freedom. But once you have the number of degrees of freedom, I do expect you to be able to use it to do something. Okay, so let's try to do that over here. Let's see how gamma connects with degree of freedom. How does gamma connect to F degrees of freedom? How should we proceed? Any idea? Go ahead.
Well, you can split Cp up into Cv, and then look at the inverse of Cv equal to 1 plus.
Yeah, you're in the right direction. You're in the right direction. Let me write it down. So what he said, what's your name? JP?
Yeah.
What JP said, I think, is that Cp minus Cv let me dock my pencil. I hate this Bluetooth pencil. Cp minus Cv is equal to Nr, right? We just showed this, where N is the number of moles. This is not number of degrees of freedom, something to remember. This is number of moles. Cp minus Cv is equal to Nr for any ideal gas, monoatomic, diatomic, triatomic, hexaatomic, I don't know, anything, because N is number of moles. So what is Cp minus Cv per mole? R, right? Cp minus Cv is equal to R per mole. So we are talking about molar heat capacity. Why? Because gamma is Cp by Cv, right? So you don't have to worry about number of moles. You could easily think about the molar heat capacity ratio to just cancel out of the numerator and denominator. So Cp minus Cv is equal to R per mole. That's one thing. And then we also know Cv. What is Cv for an ideal gas per mole? Degrees of freedom multiplied by R multiplied by 2, right? So from this, we are ready to go. Therefore, Cp is equal to Cv plus R is equal to F R by 2 plus R is equal to R multiplied by F by 2 plus 1. Therefore, gamma is equal to Cp by Cv is equal to R multiplied by F by 2 plus 1 divided by Cv, which is R F by 2 is equal to F plus 2 by F. Gamma is equal to number of degrees of freedom plus 2 divided by F. So if you knew what is the number of degrees of freedom, if you knew your quantum mechanics, you go and calculated number of vibrational states, blah, 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 all those things. Then you can calculate you can calculate something very mechanical. You're undergoing an expansion adiabatically, no heat is being exchanged, and you can calculate how will the pressure and volume change. So let's see, for example, let's write it down over here. Let's talk about a gas, its number of F and its gamma. So in this homework, you got a flavor that for a monoatomic gas, and even this is the only one which I would expect you to remember without any problem. What is the number of degrees of freedom? 3. Why? There is no constraint, right? It's a gas made up of single atoms. Everything is happily moving along. It's your life before 481. Everything was wonderful. What's going to be gamma for this one? 5 divided by 3. If we go to a diatomic gas, then you have 3 degrees of freedom, but now you have 2 rotations, 3 by 2. So it becomes 5. And in this case, you get 7 divided by 5. And you can calculate it for anything. So anytime you have a gas, so I could give you a problem, write down how does the pressure depend on volume. Write down the equation for how does pressure depend on volume for sulfur dioxide undergoing adiabatic expansion, reversible adiabatic expansion. Use the internet as far as you can, but not forgetting the answer, but use the internet to get the number of degrees of freedom for it. Or I will just give you the number of degrees of freedom. So you will take the number of degrees of freedom. It was a monoatomic gas. If it was argon, for example, so for example, argon, F is equal to 3 and gamma is equal to 5 by 3. So argon will follow PV to the power 5 by 3 is equal to constant. This is the equation that it will follow while undergoing adiabatic expansion. Again, this equation, these type of equations show up a lot, and often after in Chem 481, students tend to use this all the time. Keep in mind, this is true only for an ideal gas undergoing reversible change. Any questions about this? Go ahead. It's related, right? CV over NR was our small c. There are two constants that we introduced today, right? This is gamma. So CV over NR matters for this other equation, V to the power C is equal to constant. They are related. In the end, they are both expressible as a function of number of degrees of freedom. You can see what is this going to be in number of per mole. C is going to be F by 2, right? And this, and here, this is not molar. This is because we have divided by NR, so we don't have to, I don't know if there is a word for not molar or molar. No, I don't know. It's not molar. Let's just call it not molar. So, and gamma is equal to F plus 2 by F. And this is why this number of degrees of freedom is important. If you know how to calculate, it's complicated. It depends on temperature. It's a variety of things that affect it. But if you know what it is, you can, and if you assume ideal gas, you can calculate these things. So next time, I'm going to stop here today. I'm going to talk a little bit about thermochemistry, which is how do you measure enthalpy change in a chemical reaction? And the nice thing about that is that enthalpy is a state function. So if you have a chemical reaction going from A to C, and you don't know how to directly carry out this chemical reaction, you can split it into two reactions. You can change A to B and B to C, and you can calculate the enthalpy change for them separately, and you can still get the enthalpy change. So we'll talk a little bit about that, and then we will move on to second law of thermodynamics.